So welcome, everybody. We're Apex, and we're an API proxy for logging and controlling traffic between microservices. Today, we'll be covering 6 topics. First is, what are microservices in the first place? Secondly, challenges of working with microservices. Thirdly, some of the solutions that exist already when working with these challenges. Then we'll talk about how we designed Apex and its architecture, how we implemented Apex and deployed it, and finally, some of the challenges we ran into as we did that. So first of all, what are microservices? The thing to realize is that microservices are an architectural choice. It's an option for how you structure your system. And the other choice is a monolith. And it often is very useful to understand microservices by first talking about this other choice, the monolith. So this is what a monolith is. We show here an example of an e-commerce app on the right. So the logic for all the app is in the app server. And the app server is represented by the rectangle with rounded corners. There might also be a database. So the cylinder at the bottom right, that transfers data to and from the app server. And finally, the cloud on the top left represents a client that's talking to our app server. So that client might be a user on a web browser or on a mobile app trying to use our e-commerce app. So like in a lot of software, the logic itself within the app server is broken up into subsystems. So in Ruby, that might be modules or classes. So there might be an orders class, orders. I've got orders.js here, but it could be orders.rb for creating or updating orders. There may be a customers class for creating or updating customers, and maybe a notifications modules for sending push notifications to users. So the main takeaway here is that all of this logic runs in the same app, in one app, in the same app server. And for our app to work properly, these subsystems will need to talk to each other. So suppose orders needs to talk to customers. So on the right, you can see an arrow pointing from orders to customers. Maybe the scenario is an order just came in and with a customer ID of 85JFG and EJ. And now orders needs to find out what the name of that customer is. So it might call a method that's been exposed by the customer's module or a class or module. So remember, because all of these subsystems are running in the same app server, in fact, they're actually running in the same process in memory on the same server. And I show this on the diagram. The gray blocks represent a block of memory in the app server, and our entire app is running in that block. And because of this, because they're all running, all those method calls are happening in process and in memory, those are really very reliable and fast. And basically, as long as your code doesn't have any bugs in it, you can pretty much guarantee that that call will succeed. And one more variation of the monolithic architecture is for different systems to have their own database. So this might happen, for example, if the data that's needed by each subsystem has very different formats. So now that we understand what a monolith looks like, let's explore 2 main ways in which microservices are different. So the first is now subsystems are deployed independently. So in our e-commerce app on the right, you can see that each subsystem, orders, shipping, or all the others are all deployed to a separate server. It's as though they're all each their own app. They're no longer on the same server, and often they also have their own database. In this architecture, in the microservices architecture, these subsystems are now known as services. Secondly, services now communicate over the network. So for example, if orders now needs to create a shipment, it would make an HTTP post request to the shipping service and send. It might also send over the relevant information about the order in the body. When the shipment's been created, it's probably the case that the shipping service will now notify orders by sending back a 201 HTTP response. So even though these 2 architectures are different, so the monolith on the left and microservices on the right are very different, the idea is that they are just 2 different options for delivering the same functionality back to the user. So that was what a rundown of what microservices are. And at this point, we're probably thinking, well, what's the point? Right? Why would we choose this architecture over the monolith? And the reason why is because using the network to communicate between services gives us several benefits over the monolith. The first is a wider choice of technologies. So what I mean by that is each service's owner is now free to choose any stack that's most suited to its logic. So maybe it's the case that notifications needs to be fast, and so its owner decided to use C++. Or maybe inventory needs a lot of data analysis capabilities, so that the owner of that service chose to use Python. So they can do that as long as they stick to HTTP when talking to each other. The second benefit is that now services can be redeployed independently. So if, for example, the owner of orders decided to add a new feature and update orders to a new version, all we need to do to make that change live is to redeploy orders. We wouldn't also need to redeploy shipping and inventory and all the other services. In fact, those other services don't even need to know. As long as the API between these services remain the same, the other services don't really need to change anything about how they currently operate. And so this benefit can make it much faster for teams to ship new features to the overall system. Thirdly, and this is quite a similar benefit to the second benefit, is that each service can now be scaled independently. So suppose in our e-commerce app, orders is the first service to reach capacity. So we can scale that service only by upgrading it to a more powerful server, maybe more memory or faster processor, without having to touch any of the other services. Or maybe it's the case that shipping instead reaches capacity first. In that case, we can deploy more replicas of shipping, again, without having to also scale any of the other services. And yet again, this is only possible as long as the different services maintain the same stable API between themselves. So this makes scaling more efficient because now we only need to scale what's reaching capacity, and all the other services that aren't yet at capacity do not need more resources to be scaled. So as we can see, there's a lot to like about microservices, but using them also comes with a new set of challenges. And those challenges are all mostly because of the network, and in particular with two main fundamental limitations of the network. So the first limitation is that the network has latency. In the monolith, if we recall, when subsystems like orders and shipping talk to each other, they do so via method calls, which are really fast, usually within microseconds. Whereas when services talk to each other over network hops, those are much slower, typically tens or even hundreds of milliseconds to complete. So much, much, much slower. Second limitation of network is that it's unreliable, meaning requests or responses can be dropped at any time. So when orders cause shipping, that request could fail even if there are no bugs within either orders or shipping. Sometimes these faults are systemic, meaning maybe there's equipment failure that's causing outage for everybody, or maybe sometimes they're just random. And so because of these two limitations, two main challenges arise when choosing the microservices architecture over the monolith. The first is diagnosing network faults. So often in microservices architecture, workflows could span multiple services. So placing an order, when the client on the left places an order, that might trigger a request, a post request to orders, which then might have to check stock levels with inventory. So orders might then send a second request to inventory, and then inventory might also have to create a shipment. And so that third request from inventory to shipping represents that. And so as you can see, this cycle involves 3 requests and 3 responses, and any one of those hops could fail. And when that happens, usually as developers, our first instinct would be to check the logs. But the issue is that now, because each service is its standalone app in a way, it generates and stores its logs in a different place. And so when the developer tries to figure out what's happening, they would have to check through multiple sets of logs. They would have to first start at request number 1, check the post request in orders, see if that request failed. If not, they'd have to then check request number 2 from orders to inventory, and then see if that one failed, and so on and so forth, until they finally find the request that failed. In this case, request number 3 between inventory and shipping. So as you can see, this can be really a slow and laborious process. The second challenge that comes with using the network in microservices is managing fault handling logic. So as we've discussed, some network faults are simply random. And so sometimes instead of diagnosing every single failed request, you can just tell a service to try again a few more times. And that sometimes can work. So in this example, it's possible that even though the request from orders to shipping has failed twice already, on the third attempt, it completes successfully. And that's all good, but defining this kind of logic, this retry logic, has to be done quite carefully. And that's because, let's say if the shipping service is getting overloaded and starting to drop requests, but orders retries too soon or for too many times, that could overwhelm and crash the shipping service completely. Other times, another consideration would be sometimes we would want different retry rules for different services. So for example, maybe the case for one reason or another that we want orders when it calls shipping to wait 3 seconds between every attempt and to retry no more than 5 times. Maybe other times we want a more default rule of waiting 5 seconds between requests, but retry no more than 2 times. So all this logic has to be done, has to be defined very carefully, but where? So that logic needs to live somewhere in the system. And often this logic lives in what's called HTTP client libraries. So these are just libraries that are imported into each service's code, like a Ruby gem or a Node package. So for example, it may be the case that when orders calls shipping, that retry logic will live in a shipping client.rb gem that's required into orders' code. It's common for these libraries to not just handle retries, but also other networking concerns like rate limiting, authentication, and caching. And because these libraries have to be imported into service code, they have to be written in the same language as the service itself. So in larger teams, what usually happens is that each service has to write a new client for every language. So if shipping knows that orders and inventory and notifications all need to call it, then the owner of shipping might now want to write a client in Ruby, another one in Python, and then one more in C++ to handle retry logic and all the other networking concerns for each of those services. And this solution quickly becomes difficult to manage. As the number of services grows, each service now has to write a new library for every new language that's added to the architecture. So the number of clients can grow very quickly. Also, now updating global rules becomes much slower. Suppose the CTO now wants to make one global update to traffic rules, rate limit all services to 10,000 requests per minute. Developers would now have to update the same logic in many different libraries across many different services. That can be a very slow process that's difficult to coordinate. So in summary, because microservices rely on the network so heavily, they often come with these 2 challenges: diagnosing network faults, especially when workflows span multiple services and when the logs are distributed in different places. And secondly, managing fault handling logic that might be similar, but not exactly the same across services, but lives in multiple client libraries scattered across every service. Fortunately, some solutions exist already to handle these challenges. We'll be covering 2 main solutions, the API gateway and the service mesh. Both of these solutions are built on what's called a proxy server, but in a slightly different way. So the API gateway is just one proxy server with many extra features, whilst the service mesh consists of many proxy servers working together. So we'll be going into those relationships more in this section. So first of all, let's understand what a proxy server is. All it is just a server that sits between 2 communicating machines. So those machines could be a client or a server, or in our case, in this example, 2 services, orders and shipping. So instead of sending HTTP requests directly to each other, the order service would now send all its requests to the proxy, specifying that it wants to talk to, let's say, shipping in the host header. The proxy, seeing that request, would then forward the request to shipping. When shipping sends back a response, the proxy simply forwards this response. And with this understanding of the proxy, let's move on to exploring how an API gateway works. So here's a scenario where we have microservices, but no such thing as an API gateway. We're not using an API gateway yet. So when the client talks to our e-commerce app, it has to know the precise host, port, and path of every service in our internal system architecture. So that tightly couples the client with all our services with our internal architecture, and meaning that every time we update our services, if we happen to change the endpoint as a result, we also have to update the client. So that requires a lot of coordination between clients, the front end, and also the developers of our internal services. An API gateway solves that problem. So instead of so what it is just a proxy server that intercepts all incoming requests into the system from clients. So the benefit of that is that now we can have the API gateway provide a stable API to clients. Our services can change internally however we like. Maybe we could replicate a service or remove a service altogether or upgrade it, whatever we like. But as long as the API for clients remains stable in the API gateway, the client does not need to update. This is useful, especially if the internal system, the internal architecture gets updated very quickly by teams. Often it's the case that the API gateway also provides other features. It handles other networking concerns like authentication, caching, rate limiting. So it's useful in more than one way. It's not just for the stable API. And so an analogy I like to use to understand the API gateway is it's like a receptionist at a large company. Any visitor coming in doesn't necessarily need to know which employees are present or how employees work together. The receptionist is the person who decides whom to notify, what access to grant the visitor based on the visitor's identity and the visitor's stated purpose. So employees come and go, they could leave the company altogether, but visitors don't need to be notified. So let's remind ourselves about the challenges with microservices that we set out to solve with these solutions, diagnosing network faults and managing fault handling logic. So how could an API gateway provide a solution to these challenges? Well, for instance, we could maybe deploy an API gateway internally between services. So notice that this architecture is different to the one I presented a few slides back. The API gateway here doesn't sit between clients and services. It sits between every pair of services internally. So this isn't exactly the purpose that the API gateway was designed for, but perhaps this could be a solution for our challenges. Theoretically, yes, but existing API gateway solutions aren't quite optimal for this. And that's because it has many other features that are specific to handling client server traffic. So I've listed a few here, examples here. So maybe it would have custom APIs for different clients, maybe a different API for mobile clients, or maybe it would have a feature where it automatically generates docs for clients, or maybe it has monetization features that allow API owners to charge for API usage. All of these features are great for client server traffic, and they come built in. And so that means that when we try to use existing API gateway solutions for service-to-service traffic, those features add an unnecessary complexity for us. So it's not quite the right fit for us. However, it is still a useful pattern. It is a source of inspiration for our architecture, and we'll explain how this is so in a later section. The second solution we mentioned is a service mesh. Again, this uses a proxy server as a building block in that it uses a service mesh consists of many proxy servers working together. The service mesh has two main components, what's known as sidecar proxies and a configuration server, and we'll be explaining what each of those are. So sidecar proxies, this is a somewhat complex concept, so we approach it with an analogy. So let's imagine we have a large team in a company that has to work together, whose members have to work together, and they have to communicate with everybody. So we could have simply have this. Everybody can talk to everybody directly. Those arrows look complicated, but they're simply just lines of communication between pairs of people. So as the team grows, some of these scenarios might occur. So maybe some team members might be off sick, so anybody talking to them would have to retry the next day. Or maybe it's the case that when the team member needs a specific piece of information, he or she doesn't know who has it. So they'd have to try a few different people before they finally obtain that information. And maybe it's the case that multiple people want the same piece of information from the same person. So that person finds themselves having to provide the same response over and over again. So maybe some kind of caching will be useful there. And so managing these communication-related tasks as this team size grows can really take an increasing proportion amount of time for each team member. And that takes away time and focus from their core responsibilities. So one solution to that would be having the team members always talking through their own personal assistant, their own PA. So PAs could intercept all incoming and outgoing messages and manage communication on behalf of their team member. So you can see now all the arrows point between PAs rather than directly between team members. And all each team member has to do is just talk through their own PA. And so this frees up more time for team members to focus on their core responsibilities. So service meshes. This same topology is what a service mesh looks like. So instead of team members, now we have services. So you can see around the perimeter, we've got orders, shipping, inventory, the same services. Instead of talking directly to each other, they all talk through sidecar proxies. So these are like PAs. They're simply proxies, which we've already seen what those are, that forward requests and responses. But each service has its own sidecar proxy, and all communication flows between them. And sidecar proxies can manage things like retries and routing and caching. So recall we already discussed that retry logic has to live somewhere and has to be carefully defined. And these sidecar proxies are what enable this. And so the benefit of this architecture, in a very similar way to the team members and PAs analogy, is that the service code can now focus on its core business logic. And all the networking concerns, all the retry logic and all the other logic can be outsourced to sidecar proxies. The second component of the service mesh is the configuration server. Again, we approach this with an analogy. And so in order to do their jobs, the PAs will need to know who's on leave, right? Who's in and who's not, who has what information, who has access to what information. Maybe financial information is confidential, and so not every team member has access to that. And so all this personnel info and company policies need to live somewhere. PAs need to know about them. So one solution to that is to have one centralized folder that contains all this information. And each PA could then also get their own copy of this folder. And so whenever, and it's possible that this information changes, very, very common. So employees could leave the company, people could be off sick one day. And so whenever this information changes, we need a way to notify the PAs. So if we've already given each PA a copy of this folder, then that update has to be automatically pushed to the PA's copies. So that is essentially what a configuration server is, that centralized folder. So back in the service mesh world, that configuration folder becomes a configuration server. It contains all the information on routes, on retry logic, on rate limits, and any updates. And each sidecar proxy gets a copy of that information. And if any of that information changes in the configuration server, all those updates are automatically pushed to each sidecar proxy's cached copy. And in that way, every sidecar proxy always has the most up-to-date configuration data. So the combination of those two components, sidecar proxies and configuration server, those are what make up the service mesh. So you can see I've highlighted the configuration server, and the sidecar proxy within this entire architecture. Again, let's think back to the challenges we set out to solve with these solutions: diagnosing network faults and managing fault handling logic. The service mesh provides a strong solution to these challenges. We've got the configuration server at the top that provides us with one place to define and update logic for fault handling. And the sidecar proxies can execute all that logic and also can be responsible for logging all the requests and responses to one place somewhere else. What's more, because the service mesh doesn't have any single point of failure or traffic bottleneck, it's scalable and resilient to faults. So if any one sidecar proxy happens to fail, the rest of only its parent service goes down. All the other services and all the other sidecar proxies can continue to operate. However, this solution also comes with trade-offs. It's extremely complex because now there are double the number of components in your architecture that you have to deploy and operate. The other way in which it's complex is that sidecar proxies often are containerized. And so that changes how each service is deployed. So if any service isn't currently containerized yet, then we'd have to redeploy that service alongside its sidecar proxy in containers. So that's not always possible, as we'll see. So in summary, these two solutions embody different sets of trade-offs. The API gateway is simpler to deploy and simpler to operate, but it's not quite optimized for service-to-service traffic. On the other hand, the service mesh provides a more scalable and resilient solution, more highly available and more highly scalable, but then it's more complex to deploy and operate, and it also potentially requires changes to how services are currently deployed. So with that, I hand over to Derick to talk about Apex's design and architecture.
So after looking at the trade-offs, the pros and cons of working with an API gateway or a service mesh to solve these problems of where to host network fault logic and how to actually find a network fault, we began to think, can we do better? But it's important to ask, better for who? So as we designed Apex, we wanted to keep in mind a specific use case, a specific user or set of users who would take advantage of Apex and thus reap the specific benefits that were best for them with acceptable trade-offs. So we designed Apex for a small team that's migrating from a monolith to microservices architecture. And those microservices might already be deployed, perhaps using platform as a service environments such as Heroku. The team, having worked with monoliths in the past and just getting started on microservices, they might have a lot of experience with deploying to Heroku and want to stay in those types of environments. So we decided that Apex's architecture might look something like this, where any pair of services communicating with one another would talk through a proxy, a relatively simple proxy. And that proxy could rely on 4 additional components to achieve a full set of functionality that solves just the set of problems for us. Zooming out, the Apex architecture would look something like this. Requests would come into our system, and anytime 2 services need to communicate with one another, they communicate through Apex. So Apex becomes a central point, a critical point in the architecture. But every communication between services now goes through the central point. So we do have one place now where we can update network logic. And zooming in a little bit to that proxy, we can see that it can be made up of several different files that have different responsibilities. So if we need authentication, if we need to specify retry logic, we want to define how to log our solutions, we can have that taken care of in different places within our proxy. All requests are logged to one place, our Apex logs database. So the logging section of our middleware communicates consistently for every request and response to keep an up-to-date record in exactly one place, so that if there is a network fault or any reason to look at the history of requests, you can see that very easily in one place. Requests and responses, there may be several requests and responses that belong to a workflow where, again, where multiple services, perhaps the customer service is communicating with the order service, which needs to send a request to the shipping service, etc. All of those services need to be grouped as a part of one workflow within our logs database. So each of those requests and responses can be given a single correlation ID that helps us to understand that those logs belong to one workflow. Again, these workflows can get very complicated, but as each request and response passes through Apex, Apex can make sure that that correlation ID exists for each and every request and response in a workflow. We also want to handle the problem of having fault handling logic that may have lived in multiple places. We want to have one place for all that fault handling logic. So Apex will also need a configuration store. And that store can hold default data for how services should communicate with one another, but we can also specify different communication protocols for pairs of services. On any given request and response cycle, we can see that the Apex proxy may need to communicate with that configuration store multiple times. So we need to keep that in mind as we build our request, our solution. So Apex, a single proxy solution, compares to a service mesh very generally in this way, where Apex is fairly simple to deploy and operate since it is one core component that works together with a handful of additional components, as opposed to at least one additional component for every service in your architecture, as would be the case for the service mesh. However, there is a trade-off there, of course. That single point of failure, that single proxy in the middle between all requests, limits our scalability and can present availability problems if it were to go down. So we do recognize that Apex is not necessarily the perfect solution for every situation, but for a small team, again, that's migrating to microservices and using platform as a service, might not have the ability to containerize their different services. Apex might make a wonderful set of trade-offs. The Apex architecture is described by several vendors as a stepping stone to a full service mesh. So for a small team just starting off, you might decide to start off with just a single proxy, and then eventually, if it becomes necessary, move on to a solution where you have multiple proxies. It can be a little bit easier if you move through this stepping stone type of architecture. So what did we actually build, and how did we deploy Apex? Again, there are 5 main components to Apex. We have that main proxy server, a logs database to store all the log information, a data store for our configuration, and we also added in an admin user interface that communicates with the configuration store and the logs database through an API. For the Apex proxy, it was important that we had no unnecessary features. We wanted this to be extremely streamlined. So we built it in Node.js, which gave us the ability to handle a huge number of simultaneous requests, and it has high throughput. And we took advantage of the Express.js framework, mainly because it's minimalist, but we also appreciated the fact that it's fast and it doesn't add a lot of extra weight to our product. For the logs database, high throughput was very important. we did not want the logging of each request and response to become a bottleneck. So we chose a solution that has a high ingestion rate. Timescale DB can insert over 100,000 records per second, even if the database already has 1 billion or more records in it. For our data store, again, we might be communicating with this data store several times for each request and response. So we wanted to make sure that we could read from it very quickly. Redis would serve this purpose very well because according to Redis's benchmark information, it can process 72,000 requests per second. For our admin API, we once again turn to the Node.js and Express.js environment, specifically because Node has a rich ecosystem of third-party client libraries and allowed us to focus on the work we wanted to get done instead of building libraries. And we built the admin user face using React.js for the convenience it provides. The reusable components allow us to develop very quickly. We wanted the deployment story for the user to be as simple as possible. So we chose to deploy Apex using Docker and Docker Compose. So deploying Apex locally is as simple as cloning our repository, changing into the root directory, and running the Docker Compose up command. In implementing Apex, we did come across some interesting challenges. So we want to log every request, but what happens if we're logging extremely large request bodies? We found as we were testing the Apex solution that there were times when we were receiving, when the Apex proxy was receiving a large response body and taking extra time to send that over to the logs database. So one solution we chose was to keep the body compressed. If a body came to the Apex proxy in a compressed format, we would just send it over to the logs database in that compressed form, recognizing and accepting the trade-off that if a user needs to go and look at the logs, the user might have to decompress that log information, the body, to make it human readable. We also decided to queue the logs and send them asynchronously at the end of the request response cycle. And that allows us to open up the opportunity to optimize the way we use our database connection pool. Instead of connecting to the logs database at the very beginning of the request and response cycle, we could connect just at the end for a much shorter window and make better use of our connection pool. That would help us to process more requests at the same time through the same X proxy. We also came across the challenge of how to make sure that log and configuration data is backed up in containers. Containers are meant to be ephemeral, such that if there is a need to spin down a container, take it down, and then start it up again, you can do that. But users expect their configuration data and their log data to be persistent over time. They do not want to lose that if that container goes down. So we eventually decided upon using container volumes. Containers have the option, even though they represent an isolated environment, they do have the opportunity to use volumes to save data, to persist data to the underlying host system. And we could take advantage of that to make sure that our Redis store and our timescale DB logs could be persisted over time. In the future, however, we do plan to look into backing up with a cloud storage solution that is specifically designed to be durable over time. Take a moment to just show you what it's like to use the Apex solution. Again, one of our our first order of business is to make sure that we can proxy a request, that if we get a request from one service, we can pass it on to another service and send the proper response back. So Apex makes use of a couple of custom headers. The X-Apex authorization header allows our system to identify a specific service that is attempting to use it and authenticate that service to make sure that it has access. And the second header, the Apex responding service name, tells us which service the original service is trying to reach. So you can see here that Apex is hosted at localhost on port 1989. And the path here is the path that we would like to use to reach our destination, which in this case is CNN. In the end, you can see that indeed, although the request was sent to localhost, we were able to get back the data from CNN that we were looking for. Logging is also an important concern. Again, we want to make sure that every request and response is logged in one place so that when a network fault occurs, users can quickly and more easily take a look at the logs to find out what happened. Inside any request, the server logs for the proxy will show us that for a 200 response, the incoming request from the original service and any outgoing requests and responses are all logged to our database. Tracing is a key component of the logging because, again, when you want to examine the logs, you're likely interested in one particular workflow at a time, which we want to be able to identify with a correlation ID. So this GIF is showing us that the response to the originating service comes back with that correlation ID. And you can take advantage of our admin user interface to plug in that specific correlation ID and pull out the specific logs that you might be interested in looking at. Also, we wanted to keep all of our network fault logic in one single place. Again, our configuration store. So you can see here, we're storing default configuration and orders and shipping. When orders communicates with shipping, we have a specific set of terms for communication. The same for shipping and inventory. This configuration store is also a great place to save our credentials, to validate our services, to authenticate rather, and a good place to host the routing information so that our CNN service or our orders service can change its location and we don't have to coordinate that with any other services. If where a particular service is hosted happens to change over time, you can make the change in that single configuration store and every service can still communicate. That is also, updating that logic is also handled through our admin user interface. You can see here that we can specify for a requesting service of orders and a responding service of CNN. We can add in some custom configuration. Yeah. Thank you so much. We'll open it up to some questions now.
Okay, so Julius asked the question whether there were other databases we looked at beside timescale. We did briefly consider InfluxDB. I think our main consideration was that was in deciding that logs were a type of time series data because they're basically append only. Once you've stored a piece of logging data, you rarely want to change that piece of logging data. And when you query that data, usually the primary access is time. So we decided that logs could be thought of, in our case, as a type of time series data. And so we just went with one or the other. So we didn't really seriously consider like the detailed trade-offs between timescale and InfluxDB, but we just went with a a common choice, one of the common choices for time series data in timescale DB.
So Julius asks, what was the most difficult part of the project? And I'd have to say that the hardest part of the project was probably the initial research, of going through the process of seeing a problem and not just recognizing that it represents a problem that, that developers might have to deal with, but painstakingly going through the process of understanding all the trade-offs and the different types of solutions that exist, and then bringing that understanding to the process of crafting a solution that's narrowed down to a specific user, knowing that we can't just build something that's going to work for everyone. Extremely challenging.
I'll probably agree with that. I think especially for me, understanding the different types of existing solutions and how they work, the API gateway and the service mesh. There were a couple of other solutions as well, and often they're clouded in enterprise software speak. So it's hard work to figure out what the actual architecture and what components are included in those solutions. And that for me was probably the most difficult part. The actual building, once we understood the problem, wasn't too difficult. So yeah, very much agree with Derick there.
Yeah, I'll put an asterisk on that though, and say that we did want to make sure that this process, that our solution was very easy for users to deploy, and getting it to work properly in a containerized environment was new and challenging as well.
So Mike asked, are you able to give us a taste of how you tested throughout development? That's been very difficult for us, to be quite honest. It's not like, because what we were building wasn't just, say, one React app or one Rails app where we could just run the test suite. A lot of it depends on how it's actually used in production, the kind of traffic we're anticipating, and the kind of types of faults we're anticipating. Those were very hard to simulate. That said, we did one way we did what we were able to test the retry logic was using a very small timeout value. So that was quite convenient because the timeout in our Redis store in the configuration defines what we class as a failed request. So what do we mean by a failed request, right? So is it, do we have to wait 30 seconds, or maybe does it have to be a 404 that comes back? So we defined that. So the timeout was what defined that. It defined how long each requesting service is willing to wait before or how long Apex was willing to wait before just calling a request failed. So we were able to test the retry logic by simply setting the timeout to a super small value, maybe 1 millisecond or 10 milliseconds. But we did struggle to go a lot further in running tests.
Testing was extremely challenging before we were able to Dockerize our solution. So once we were able to get everything working all together in Docker, it was relatively easy to run the command to spin up the application and touch anything and see what was happening with it. But before that, it really was a lot of using a tool such as Postman and trying to think about the specifics of what makes sense for a request, trying to emulate a request coming from one service going to another, what that might look like.
Emil, sorry if I'm abusing your name. You asked, were you guys able to test how many services can simultaneously work for this solution? So I think the metric that really determines, I think like just the number of services isn't the only metric that matters, because it also depends very much on how heavily each service is making requests and responses. So we weren't able to do too many tests, but I think what we estimated was that we'd be able to take probably the bottleneck. So either in a single request response cycle, every request would have to at least go through Node and then also Redis. So both of those are designed to handle a lot of a very high read rate. So the way to figure out the answer to how many services can simultaneously work would be to just take the smaller of those numbers and maybe divide that by by a factor of maybe by an order of magnitude or so, just because the whole point is that some requests might fail, might have to be retried. And so so the practical, the actual throughput would definitely be lower than much lower than those theoretical limits. And so that's the way we could theoretically work out the answer to that question, but we weren't able to test that in the time we had.
Yeah, doing thorough load testing would probably require dreaming up several different scenarios for how different teams might use our system. And it's hard to imagine that a scenario where there are perhaps just a few services, sending requests and responses that may include, say, audio data, so very large response patterns. It's hard to see how that might be relevant for a team that has very quickly added many services that are perhaps just sending a little bit of text data. So were a lot of variables to take in mind, to keep in mind. But these are some of the reasons why we wanted to think about the footprint of our proxy and say, we don't want a large system with a lot of extra unnecessary features running in our environment, because we feel it's not going to be able to handle as many concurrent requests. So those types of considerations certainly came into play and were at the front of our mind as we were developing the solution.
I guess a final addition to that is, if you think back to our use case, the use case that Derick described at the beginning of section 4, our design and architecture, we specifically didn't want to design for the case where a large team uses dozens and dozens of services. We think by that point, they should probably migrate to a service mesh, which Apex helps them with, as Nginx and other vendors described. And so that is one additional consideration there in terms of trying to use Apex for really a very large architecture, is that probably Apex isn't the right solution when teams reach that size.
So
Okay.
does Apex support service discovery? So out of the box, right now, no, Apex does not support service discovery. Again, we considered our use case for a small team that's just getting started. Now, they may very rapidly grow to the point where a team may very rapidly grow to the point where they want to implement service discovery. So that can be done in two ways. The Express, the node proxy using Express.js applies what's known as the middleware pattern. So users can add their own custom logic to the Apex proxy fairly easily. They can add and remove the features that they want. Second, if you're running your, if you need essentially load balancing for service discovery, if you, instead of adding the direct network location of a particular service, such as the CNN or the order service, if instead you give Apex the network location of the load balancer, Apex can forward that request over to the load balancer, and the load balancer can take it from there.
That said, it's certainly possible. I think one of the beauty of having having one proxy that mediates all service-to-service traffic is, as Derick mentioned, that middleware pattern that allows us to add more features. So certainly, we did consider adding service discovery, but we stopped at routing. We stopped at we felt that was already enough for our users, given that they, one of our trade-offs was not to prioritize high scalability and high availability. So I guess the short answer is it's certainly possible, but we in the end decided that wasn't quite what our users needed yet.
So Ron asks about the trade-offs for Apex versus other solutions, and the fact that we were thinking about not adding quote unquote extra features. So how did we decide which features we would add? That's always a tough challenge. But when we were first conceiving of Apex, we said, there's no way we're going to be able to think of everything that everybody is going to want to use a product like this for. So we chose the Express.js framework and that middleware pattern to allow, just to specify, the middleware pattern means that when a request comes into the system, each piece of middleware in turn has a chance to take a look at and process the request and the response. So to do something with the information that's passing through, one at a time. So a user can add in new functionality very easily. Add, test, and deploy. If a user does not want, say, the logging functionality, the user could very easily remove that. The user could add different routes through the system to manage different types of workflows that might have different requirements. So it really came down to what were the core features we wanted to have in Apex. And the two things that we wanted to do more than anything were make sure that when a network fault does occur and a message gets dropped somewhere in a complex workflow, a user has the ability to go look in one place and examine those logs and perhaps more quickly and more easily understand what happened. The other thing we wanted to do was make sure that users were able to customize the different types of rules they might want to have for communication between any two pairs of services. So having built those two pieces of functionality, we rounded out the rest with some requirements such as authentication and routing to build just the features that cover that use case that we described.
Well, one thing we did think about, but we ran out of time for, is because now currently on every request, our node proxy, Apex proxy, has to query the configuration store multiple times. First for authentication, just to verify the identity of the requesting service. Secondly, the second time for routing information. So if someone gives us CNN as the header, we then mash that to www.cnn.com. And finally, the third time for to fetch configuration data, retry logic. So you can see, you can imagine that if every request queries Redis 3 times or up to 3 times, then that could multiply the read rate very quickly. So we did consider caching what's on Redis within Apex proxy so that we don't have to query Redis every single request on multiple times on every single request. But that, of course, creates another problem where if the configuration data updates, we have to find a way to also update the cache within Apex proxy. So that was something we did consider, but eventually didn't get around to doing. So I think that's all we have time for. Any other questions?
Thank you so much for attending today. Feel free to reach out to us directly. I am Derick Gross, and work together on this project with Kelvin Wong. We would be honored to speak with you further about the project. Thank you so much for attending today, everybody.
It is all on Slack. Great. Thank you, everyone. Have a good day.